Hello once again, complex analysis students. Today we're going to be talking about the exponential form of complex numbers. And as part of that discussion, we'll talk about something called the arguments of complex numbers, and we'll also talk about nth roots of complex numbers. To get the ball rolling on that, we're going to first focus on the polar form of a complex number. You may remember polar coordinates from your calculus sequence. That's exactly what the polar form of a complex number is, just sort of written in a complex form. I've got this point here, z equals x plus iy, and as you know, that's really the point x comma y, and we could talk about the polar coordinates of that point, so we could think of it as r comma theta. So what are polar coordinates? Let me remind you of how that works. So the polar coordinates of a point, you have r and you have theta. So r is just the distance of that point to the origin, so it's the length of this line from z to the origin, and theta is the angle that that line labeled r there makes with the positive x-axis. So really, r here is just the modulus of z. And theta, so if you look at this little triangle inside this picture here, there's a triangle here. The bottom side of that triangle has length x, and the vertical side of it has length y. But through a little trigonometry, cosine of theta is equal to x over r. So I can solve that for x, and I get x equals r cosine theta. Similarly, y is equal to r sine theta. And that theta is determined by two things, really. Let's say theta is the angle in the quadrant of z, satisfying tangent of theta. If you look at that angle, tangent of theta, it equals y over x, right? So that's sort of a key relationship between the angle theta and the regular rectangular coordinates x and y of our complex number. So the polar form is just where you replace x and y with the r cosine theta and r sine theta. So instead of x plus iy, I'll have r cosine theta plus I times r sine theta. Or if I just factor the r out, I can write it like this. It's r times cosine theta plus I sine theta. So here is your polar form. And the polar form's nice because you can look at it if someone writes it out that way, and you can instantly see, oh, you know, it makes it easy to sort of locate the point. You know what its angle is, you know what its radius is. But it's certainly that angle theta, the problem always with polar coordinates of a point is that if you think about that, let me go back up here to the top. When we were looking at the polar coordinates r comma theta, the angle theta, I mean, if you just start adding multiples of 2 pi to that angle, you get the same polar coordinates. It describes the same point. So theta is certainly not unique. All we know is that tangent of theta equals y over x. And there are lots of angles theta where tangent of theta equals whatever the y over the x is. So an argument of our complex number x plus iy is just any angle in the quadrant of z satisfying tangent of theta equals y over x. So there's those two things. The angle has to be in the right quadrant, and then when you plug it into tangent, you have to get y over x. That's what makes it an argument of our complex number. And then we use this notation argz to indicate any possible argument. So argz is the set of all arguments of z. So all the arguments of z, they're all just, once you find one of them, then you just add multiples of 2 pi to any argument to get all the other arguments. So one of those arguments is called the principal argument, and the principal argument is just that one special argument that falls in a certain interval that we're interested in. So the principal argument of z is the argument of z, let's call it capital theta, that falls between negative pi not inclusive to positive pi inclusive. The argument of z is just any one of those angles that you get when you put the complex number into polar form. The notation argz here indicates all the arguments, so there's a whole collection of them where they're just all separated by multiples of 2 pi. And then there's the principal argument. It's just that one special argument from all the infinity of arguments that you have for z that fall in this particular interval here. Negative pi to positive pi, left-hand endpoint not included, right-hand endpoint included. So there's a little bit of a relationship here then that we can make note of. Argz as a set. This will seem like kind of strange notation, but let me abuse notation a little bit because that's the way the book does it. But you can think of argz, the set of all arguments is just the principal argument plus 2 times pi times n, where n is just any integer. It's a little bit of an abusive notation because on the left-hand side there, that's a set. But argz is just a number. Probably a more accurate way to say this would be argz equals the set of all thetas, where theta equals the principal argument. Oh yeah, I forgot to mention the principal argument. We use this notation capital ARG. Let me squeeze that in here. Capital ARG of z is the principal argument. Thing that we were doing at the bottom there, any argument is just the principal argument plus some multiple of 2 pi. Maybe we should see an example here that kind of makes it clear what we got going on. So here I've got the complex number negative square root of 3 plus I, which I've taken the liberty of graphing ahead of time. Let's look at the polar form of that number. We need to calculate the radius, indicated here with this blue line. And we need to calculate theta, that angle there. R, that's just the modulus of z. And the modulus of z is you take the square root of the sum of the squares of the components. So you'd get negative square root of 3 squared plus 1 squared. So that just works out to be 2, right? Now how about theta? All I know is that tangent of theta is the y over the x, and the y is 1, and the x is negative square root of 3. So I have to think to myself, I mean, yeah, you could go run and punch this into a calculator, I suppose, but unless you have a symbolic calculator, it's just going to return like some decimal value. But I would like to get the exact number, and I can get it because this is one of those special angles. You can probably guess what that angle is just by kind of looking at the picture, but I know that if I want to get 1 over negative square root of 3, I could do that as doing 1/2 over negative square root of 3 over 2. And I know tangent is the sine over the cosine. So if I'm thinking this is the sine of theta and this is the cosine of theta, what would theta have to be? Well, since I know the values on the unit circle for sine and cosine, I know sine is 1/2 and cosine is negative square root of 3 over 2, and the angle theta is equal to 5 pi over 6. Theta equals 5 pi over 6 is an argument. But moreover, it's the principal argument, because it's in the right interval. It's in between negative pi and positive pi. All right, so now what's the polar form of this complex number? Well, it's easy. We've got the radius, 2, and we've got the angle, 5 pi over 6. We've got an argument. So all you got to do is it's just z equals the radius is 2 times cosine of 5 pi over 6 plus I times sine of 5 pi over 6. And we could look at argz, little a, like just the regular argument. So that's a collection of all of those angles that are arguments of z. So the way you could describe that is just the set of all angles of the form 5 pi over 6 plus 2 pi times n, where n is any integer. Now, in the textbook, he typically doesn't describe it as a set. He just says, he just kind of abuses notation a little bit. He says argz is 5 pi plus 2 pi n, and then just writes, n as an integer over here. So you can write it that way if you want. Technically, you should describe it as a set. But, I mean, in context, we kind of know what you're talking about if you write it this way. That's describing a whole bunch of arguments if you put 2 pi n, where n is any integer. All right, so now that we have the polar form, and we understand, every complex number can be associated with a radius, a positive radius, and then some sort of angle, then we can start talking about the exponential form of a complex number, which is actually more useful. Sort of the polar form is just sort of a intermediate step to get there. So the first thing we want to talk about is so-called Eulers Formula. It says that when you do e to the I theta, that means the same thing as cosine theta plus I times sine of theta. For now, you should interpret this to mean, when you see this e to the I theta here, just think of that as a single symbol instead of thinking of it literally as the number e raised to the power I theta, because what does that even mean? What does it mean to raise the number e to the power I theta? We haven't even defined what that means yet. And we're going to later define exactly what we mean by that. But for now, we haven't really defined, what such an exponent would even mean. So just interpret the whole symbol e to the I theta as just a single thing, and we're just defining it. E to the I theta is defined to be, that's why it's a colon equals there, cosine theta plus I sine theta. Now, of course, it really is e to the I theta. We'll find out later. It really is the number e raised to the power of I theta. It does work out to be cosine theta plus I sine theta magically. There's a kind of a cool way to see this in terms of Taylor series also. Like if you take the Taylor series for e to the I theta, or if you take the Taylor series for e to the x and you plug in I theta, you can see that this is what it boils out to. But anyway, don't worry about that right now. You just kind of have to take a little leap of faith that this is the right notation that we should be using. So anyway, that's Eulers' formula. When we put a number into its polar form, which I've done right here in green, well, look, inside the parentheses there, that's the right-hand side of Eulers' formula, right? So that means that the complex number that you started with, z equals x plus I, y, if you figure out what its r and its theta are, then that means you can write that complex number in the form z equals r times e to the I theta. This is what we call the exponential form of z. And this is a very handy-dandy way to look at complex numbers. Let's see that we understand the concept with just a very concrete example. So here's the complex number -1 minus I, and I want to put it into its exponential form. If you want to find the exponential form of a complex number, you just got to figure out what its r and its theta are. It's essentially just doing the same thing as getting the polar form of it. You just write down the formula a little differently, but you got to find r and you got to find theta. It's helpful to think about it geometrically for me. So I'm just going to graph this number in the plane. Well, you can tell just by looking at it that that's a 45-degree angle down in the third quadrant. So it's apparent that r is the hypotenuse of a right triangle with legs of length 1. So you can pretty quickly see here that r is equal to the square root of 2. And your angle theta, I would probably do 5 pi over 4, because I tend to think of angles between 0 and 2 pi. So we could write z in the form square root of 2 times e to the I times 5 pi over 4. That's a perfectly fine representation of that number. Sometimes, though, we like to use the principal argument for our angle. So we could do, we know arg z, the principal argument. Okay, if I want to get the principal argument from 5 pi over 4, I could just subtract 2 pi from it. And if I subtract 2 pi from it, it would be negative 3 pi over 4. So that would give me the angle that's between negative pi and positive pi, right? So I could also do z is equal to the square root of 2 times e to the I times negative 3 pi over 4. And you can kind of think of that, the last way I'm writing it here is sort of like the standard way to write that number. But both are fine. They're equal to each other. So in summary here at the bottom, the rectangular form of a complex number is just your x plus iy. The polar form is r times cosine theta plus I sine theta, where r is the modulus of z. So that's the square root of x squared plus y squared. And tangent of theta is y over x. And theta is in the quadrant of z. And the exponential form is z equals r times e to the I theta, where again r is the modulus. And tangent of theta is equal to y over x. And theta is in the quadrant, in the appropriate quadrant. So I put a dotted line between polar form and exponential form because I feel like they're really the same thing. But yeah, they look a little different, but it's really the same stuff. So those are the three ways that we tend to describe complex numbers. And we use whichever one is, you know, the most convenient. Just like you did in calculus. Like sometimes an integral is easier to do if you convert it to polar coordinates, or if you can convert it to cylindrical coordinates or whatever. So you just do what's most convenient. One thing we see is that circles have a nice description in terms of exponential form of complex numbers. So first of all, if we would look at the equation, z equals e to the I theta, where I think of theta as being the variable that changes, the parameter. If you think about it, see e to the I theta is just cosine theta plus I sine theta. Or if you want to think of that as an ordered pair, it's cosine theta, sine theta. Well, that's exactly the unit circle, right? That's how we describe the unit circle. Okay, and now if we take the previous thing that we had and multiply it times some real number r and get this equation, so it's very similar to the previous equation, just multiplied times r. So r here is a fixed real number that's positive. And again, theta is the parameter that's changing. Then we get a circle, but this time it's a circle centered at the origin of radius r. And then lastly, if you see an equation of this form, and this time z naught is a fixed complex number, r is again a fixed positive real number, and theta is the variable, the parameter, then this time you're going to get a circle that's been scooched over by the vector z0. So remember, we can think of z0 as a vector. So let's say here's z0. Centered at z0, I can draw a circle of radius r. And you can see that a general point on that circle, you can think of it as a sum of two vectors. z0 there in green plus, then go from the end of z0 and go by r e to the I theta, which, would put you on a circle of radius r, or would put you at, put you a distance of r away from z0. So you'd be on a circle centered at z0 of radius r. So for example, what am I looking at right here in this equation at the bottom? You can see it's just the situation where the z0 is equal to 3 and the big R is equal to 2. So we could graph this in a jiffy. We can see that this is a circle centered at 3, which you can think of it as the point 3 on the x-axis, and then you got a circle of radius 2 there. So you would get that circle. As you may remember from your algebra class from way back, exponential functions have nice properties, like when you multiply them and you divide them. Using this notation e to the I theta, it's really going to act like an exponential function. For example, this first property here, what should you get when you do e to the I theta 1 multiplied times e to the I theta 2? Well, the way you did these things with real numbers is you just added the exponents. And that's exactly how we'll do it now. It works out to be e to the I theta 1 plus I times theta 2, which you can simplify by factoring out the I as e to the I times theta 1 plus theta 2. This is something we would need to verify, but we can. It's not hard to prove. It just comes down to multiplying out the appropriate expression, because we know what e to the I theta 1 is. That's cosine of theta 1 plus I times sine theta 1. And similarly for the theta 2, you just multiply it out and see that it works. You got to use some trigonometric identities, but it's not super hard. And then once you have, that's how it works with just Eulers formula, then you can put the radii, start adding in radii. So if you have z1 is equal to r1 e to the I theta 1, and z2 is r2 e to the I theta 2, then z1 times z2 is just going to be r1 times r2 times e raised to the I times theta 1 plus theta 2. And if you do z1 over z2, assuming z2 is not 0, then you would get r1 divided by r2, and then you're going to get e to the I times theta 1 minus theta 2. These exponential forms of complex numbers are acting exactly the way you would think they would with respect to multiplication and division. And, sort of special cases of this, if you look at the inverse of z to the negative 1, we know that we can kind of think of that as 1 over z. So what you're going to end up with is 1 over r e to the negative I theta. It wouldn't be hard to do an inductive argument to show that when you take z and you raise it to the n, you're going to get r to the n times e to the I times n theta. But I hope what you're recognizing here is that these complex numbers are acting just like real numbers act. And a special case of this raising things to the nth power is if you just take e to the I theta, so the radius is equal to 1, and you raise that to the nth power. Well, according to our exponential formula that we just did right here, we're going to get e to the I times n theta. But when you convert back to polar form, you get something kind of interesting looking here. It turns out that if you take cosine of theta plus I sine theta and you raise that whole thing to the nth power, you just end up with cosine of n theta plus I times sine of n times theta. You really have to pause for a second and appreciate this formula right here. It's pretty impressive. You get it almost for free just because of the way exponents work. If you had a complex number in the form cosine theta plus I sine theta and you wanted to raise it to the 100th power or something like that, it would be a big drag. You would not want to have to multiply something like that out 100 times. It would not be fun. But you don't have to. The right-hand side of this formula, just whatever the power is, you just put it in front of theta, and it's a small computation. Let me give you an example of this. If you take cosine theta plus I sine theta, you raise that to the second power. According to de Moivre's formula, that's supposed to be cosine of 2 theta plus I sine theta, I sine 2 theta. But the left-hand side, since the exponent's only 2 there, we could actually multiply that out. It wouldn't be a big deal. So if you multiply that out, you'd get cosine squared of theta plus 2 times I times cosine theta sine theta, plus then you get I squared sine squared theta still equals cosine of 2 theta plus I sine 2 theta. You've got an I squared there, so if I combine the real parts, I'd have cosine squared theta minus sine squared theta plus I times 2 cosine theta sine theta equals cosine 2 theta plus I sine theta. We learned early on that two complex numbers are equal exactly when the real parts are equal and the imaginary parts are equal. So that tells me that this real part over here has to equal this real part over here. So cosine squared of theta minus sine squared of theta equals cosine of 2 theta. And similarly, the imaginary parts have to be equal. So sine of 2 theta has to be equal to 2 cosine theta sine theta. So we've just derived double angle identities for sine and cosine. It's kind of cool. It just fell out of this thing. So you get cosine 2 theta equals cosine squared theta minus sine squared of theta. And sine of 2 theta, usually we write that as 2 sine theta cosine theta. And those are the double angle identities. The double angle identities aren't super hard to derive from scratch in trigonometry class either, but it's kind of cool that they just fall out. And you can imagine cubing things and raising things to the 4th power and 5th power and so on, and you could get like triple angle identities and quadruple angle identities. And in fact, I think the challenge problem on your homework is along these lines. Okay, in the next example, I just want to, I have this complex number and I'd like to raise it to the 8th power. But man, I don't want to do it while that number is in rectangular form, because look at it. Yuck. I do not want to raise something to the 8th power. That means I got to multiply that thing out 8 times, and I'm just not going to do it. But if I convert it to exponential form, it's quite easy. So step 1, let's convert this thing into exponential form. I can see from the form of it that it is in the 4th quadrant because the real part's positive and the imaginary part's negative. So there's the complex number graphed as a vector. So I can see that r is the magnitude of this, 1 minus I squared of 3, which is the square root of 1 squared plus negative square root of 3 squared. So that works out the square root of 4, which is 2. And then tangent of theta is equal to the y over the x. So that's negative square root of 3 over 1. And here I want to make note that theta is in quadrant 4. And so, I got to think. I always think, okay, I got to have something that's like negative square root of 3 over 2 over 1/2. I want this to be sine of theta, the negative square root of 3 over 2, and I want this down here to be the cosine of theta, so that'll work out to just be negative square root of 3 if I take the tangent of it. So it looks like that angle is going to be negative pi over 3. I mean, I could have said like 5 pi over 3, but that wouldn't be the principal argument. That would just be an argument. But in any event, so there's my angle. So then I can say 1 minus I times the square root of 3 is equal to 2 times e to the negative pi over 3 times I. And now raising this thing to the 8th power is not a big deal. 1 minus I squared of 3 to the 8th power would be 2 to the 8th. And then e to the 8 times negative pi over 3 times I. So that's 2 to the 8th e to the negative 8 pi over 3 times I. Negative 8 pi over 3 seems like kind of a strange angle, but negative 8 pi over 3 here, you can express that as negative 2 pi minus 2 pi over 3. So see that negative 2 pi, I'm just adding a multiple of 2 pi to that angle, so I can sort of just throw that away if I want, and just write this as 2 to the 8th times e to the negative 2 pi over 3 times I. But the point here is that I didn't really have to like sit here and do this, like 1 minus I times the square root of 3 times 1 minus I times the square root of 3 times ... 1 minus I times the square root of 3, 8 times, and then actually do all the multiplication to figure that out. Converting it to polar form made it super easy, so didn't have to do that. We want to see how arguments are related to, products and quotients. So we'll start with, a couple of arbitrary complex numbers. Z1 equals R1 e to the I theta 1, and Z2 equals R2 e to the I theta 2. When you multiply Z1 times Z2, we know how to do that multiplication, right? Let me do it at the top here. Like z1, z2 is r1, r2, e to the I times theta 1 plus theta 2. So it's probably not surprising to you then that if you look at the argument of z1, z2, it is the argument of z1 plus the argument of z2, just because of that sum that you get up there at the top, right? Now, that's not a proof. The proof of it's actually a little bit more of a pain because we have to think back to the definition of arg. So little a arg is a set, right? So what we're really saying is the set on the left here, arg of z1 times z2, is equal to arg z1, that set, plus arg z2, that set. And what do we mean by plus in the middle? Well, from context, you can understand that that means to take the elements in the first set and add to them the elements in the second set. So take all the possible sums of the elements of those two sets. So that would be something that needed to be proved. But it's based on this idea that, you know, when you multiply the complex numbers, you end up adding the angles. In a similar fashion, the arg of z1 inverse, well, remember z1 inverse would be the same as 1 over r1, and then you'd have e to the negative I theta 1. So when you invert a complex number, it just negates the argument. So this is going to end up being negative arg z1. And then for the quotient, it's essentially put together the first observation and the second observation, and you'd get arg z1 minus arg z2. So I was thinking I'd prove that first relationship there. Well, I'm going to do this a little differently than the way the textbook did it. I want to go back to thinking of those as sets. And so if I want to prove two sets are equal, I can do a proof by double containment. So if I took some number, let's say theta, and I say it's in arg z1, z2, z1, z2 is equal to r1, r2, e to the I times theta 1 plus theta 2. So theta 1 plus theta 2 is an element of arg z1, z2 also, right? But what do we know about arg z1, z2? That's the collection of all the arguments. And we know that they're all, the difference between them is 2 pi, some multiple of 2 pi. So that tells me that theta is equal to theta 1 plus theta 2 plus some multiple of 2 pi. We could do a little trick here. We could just sort of split n up into two integers. So let's just let n equal n1 plus n2, where n1 and n2 are integers. I mean, for example, n1 could be equal to 1, and n2 could be n minus 1 or something like that. There's lots of choices you could use for n1 and n2 here. Doesn't really matter. So now we have theta equals theta 1 plus theta 2 plus 2 pi times n1 plus n2. So what I could do is just distribute the 2 pi over the n1 plus n2, and then group things slightly differently so that I'd have theta 1 plus 2 times pi times n1 plus theta 2 plus 2 times pi times n2. If you look at what theta is equal to here, theta is equal to theta 1, which is an argument of z1 plus a multiple of 2 pi, and then theta 2 plus a multiple of 2 pi. So this is telling me right here that theta is in the set of arguments of z1 plus the arguments of z2. Reversing the argument, if theta is in arg z1 plus arg z2, I mean, basically you're just going to reverse the steps of the previous argument. You'd say, well, there exist n1, n2 in the integers such that theta is equal to theta 1 plus 2 pi n1 plus theta 2 plus 2 pi n2. But then you could write that as theta 1 plus theta 2 plus 2 pi times n1 plus n2. So theta is an argument. See, theta, we've expressed it as an argument of z1 times z2 plus some multiple of 2 pi. So theta is an argument of z1, z2. And the other arguments would be very similar to this sort of argument. So it's not super hard. I think the cleanest way to do it here is just to do a double containment argument. Okay, so let's have a look at an example here that kind of illustrates how these arguments are related to one another. Tried to pick some kind of easy to visualize complex numbers. -1, let me draw a quick and dirty picture over here. Z1's over here, just -1, and Z2 is I. So you can see that this, if you think of -1 as a complex number here, theta 1 is equal to pi. And likewise, if you think of I as a vector, that angle is pi over 2. So we can see that z1, you can express that as 1 times e to the I pi, and z2, you can express that as 1 times e to the pi over 2. We know as a general property that the arg of z1 times z2 is equal to the arg of z1 plus the arg of z2. But arg is, these are all sets, right? So what we're saying is that arg of, okay, what is z1 times z2? That's negative I. Should be equal to the arg of z1, which is negative 1, plus the arg of z2, which is I. Like, I know that pi is an element of that first set, and I know pi over 2 is an element of that second set. So what's an argument of I? Negative I. Tells me that pi plus pi over 2 is an element of the argument of negative I. In other words, 3 pi over 2 is an element of arg of negative I. On the other hand, so since I know 3 pi over 2 is an arg of negative I, then I know that I can write negative I is equal to, would be e to the I times 3 pi over 2. But another thing to observe is that it's not true that the principal argument of z1 times z2 is not necessarily the same as the principal argument of z1 plus the principal argument of z2. Because what is the principal argument of negative I is actually negative pi over 2, because the angle has to fall between negative pi and positive pi. But we already know that the principal argument of z1 would be pi, and the principal argument of z2 would be pi over 2. Negative pi over 2 is not the same thing as pi plus pi over 2, because the right-hand side is equal to 3 pi over 2. So this relationship holds for the regular args as sets, but it doesn't translate into being an equation for principal arguments, okay? Okay, so here's another example. So here's z equals I over 1 minus I. And I suppose if I wanted to, I could do the arithmetic to write that in the form a plus b times I. But we can actually see what the argument of this complex number is without doing that. Because let me think of the numerator here as z1 and the denominator as z2. What is the argument of z1? The argument of I. Well, we just did that a minute ago. The argument of that is pi over 2 plus 2 pi n1, where n1 is an integer. And argument of z2, I think you can see that negative 1 minus I is a third quadrant complex number, and it's at a 45-degree angle down into the third quadrant. So its principal argument would be negative 3 pi over 4. So if I wanted an argument for this I over negative 1 minus I could just, subtract, because I'm doing division. So it'd be like pi over 2 minus negative 3 pi over 4 plus 2 pi n. So see, I'm just taking arg of z1 minus, you end up with 5 pi over 4. So since I know this is one of the arguments of that complex number, then it would make it easier for me to write it into exponential form. I'd have to find its radius. I'm not going to bother with that at this point, but the point is that I can see what its angle is without really having to do very much work. I could just deduce its angle from the angle of the numerator and the angle of the denominator, which is kind of cool. Okay, the last topic that we're going to talk about in this lecture is the topic of roots of complex numbers. So a little preliminary, when we have our complex numbers in exponential form, like we have here and here, z1 equals r1 e to the I theta 1 and z2 equals r2 e to the I theta 2, we know that those representations aren't necessarily unique because the angle you can just add multiples of 2 pi on. But we still want to know, how do we tell when two complex numbers in their exponential form are equal? Well, they're going to be equal exactly when they have the same radii. So we have r1 equals r2, and those two angles just need to be multiples of 2 pi apart. So we could say something like, and theta 1 has to equal theta 2 plus some multiple of 2 pi. So this is how we tell if two complex numbers in exponential form are equal. Same radii, and the angles are multiples of 2 pi away from each other. So that's important as we go forward because, well, you'll see. It'll come up here in a second. So now I want to talk about the nth roots of z naught. So z naught is just some complex number. But what do I mean the nth roots of z naught? Well, just like in the real numbers, when you say something's the square root of whatever, square root of x is just, the square root of x is just any number that you square and you get back x. So the nth root of z naught is just the same idea. It's any number that you raise it to the nth power and you get back z naught. The nth roots of z naught are just the solutions to the equation z to the n equals z naught. I want to figure out, what are those nth roots? What are those values of z that satisfy that equation? So I want to solve this equation. So to solve that equation, I'm going to put those complex numbers z and z naught into exponential form here and here. And so then what does that equation become when you substitute in? Well, the left-hand side, you'd have r to the n equals e to the I times n theta. And then on the right-hand side, you'd have r naught times e to the I theta naught. We just said up here in yellow that when two numbers in this sort of exponential form are equal, what does that mean? Well, it means that their radii are equal, and it means that the angles are separated from one another by a multiple of 2 pi. From here, I can deduce that I have r to the n must equal r naught, and n times theta has to equal theta naught plus 2 times pi times n. So I'm just equating the radii and the angle, the thing that's multiplied times I, and the exponent. And the first equation, I can take the regular old real nth root of both sides of that first equation, and I get r has to be the nth root of r naught. And by this, I mean the unique nth root of this r naught, which is non-negative. And I can solve for theta in that second equation, and theta would have to be theta naught over n plus, I double dipped on using n. I should have used a variable k here. But dividing both sides by n in that equation involving the angles, I'd get theta equals theta naught over n plus 2 pi k over n. So that means that we've just found our nth root. We've solved the equation. So the solution is z equals the nth root of r naught times e to the I times that theta, which is theta naught over n plus 2 pi k over n, where k is an integer. And it makes it look like there are infinitely many different nth roots, but what you notice is that, if you started the counter k at 0 and worked all the way up to n, then you would get plus 2 pi, and so that would be a repeat of a previous angle. And if you put in k equals n plus 1, you would get 2 pi plus, you could sort of write it as an improper fraction and keep pulling off a multiple of 2 pi. So you get, as you start running k through all its possible values in the integers, you get a lot of repeated values. So we get repeated roots over all k in the integers. So the unique ones are just these. ck equals the nth root of r naught times e raised to the I times theta naught over n plus 2 pi k over n, where k is equal to 0, 1, 2, all the way up to n minus 1. By the time that you get to n, you get a repeat, and then n plus 1 would be a repeat of something that you had previously. So these are the nth roots of z naught, which is r naught e to the I theta naught. And c0 is the principal nth root. So just let k equal 0 in that expression, and you get the one special one we call the principal root. Let's see how this works. I'll recopy the formula down here for how to get the roots, since it was on the previous page. Let's try this with z naught equals negative 16. I want to find the fourth roots. Well, to do this, the first thing you need to do is to put that number into its exponential form, and that's pretty straightforward. The exponential form of z naught is just z naught equals 16, and since it's negative on the negative x-axis, that means its angle is pi, so this will be e to the I pi. In this formula up here, your theta naught is equal to pi, and your r is equal to 16. So basically, you just got to take this information and put it up here into this formula at the top. We're going to have a c0. The counter starts at 0 and goes to 4 because we're doing fourth roots. So c0 would be the fourth root of 16 times e times I to the theta naught, which is pi, over 4 plus, and then 2 times pi times 0 over 4. And so the 4th root of 16 is 2, and then this would be e to the I pi over 4. And then you have that 0 times stuff up there that just goes away. So by the way, this is the principal 4th root, because the angle that I started with, theta naught, was the arg. So I got the principal 4th root, and then C1 is the 4th root of 16 times e to the I pi over 4 plus, then you just put k equals 1 in there, so you get 2 pi times 1 over 4. So in other words, the angle is pi over 4 plus pi over 2, so that'd be 3 pi over 4. So that's 2e to the I 3 pi over 4. So I'd probably write that as just 3i pi over 4. And then the next one, I think you can check for yourself that it's going to be 2 times e to the 5i pi over 4. And the next one after that, C3, is 2e to the 7i pi over 4. So like you could kind of keep going with this. Remember I told you that you get the unique ones by using the values from 0 to n minus 1. But if you would keep going, like let's say I did C4, it's really going to end up being the same thing as C0, because C4 would be 2e to the 9i pi over 4. But that's the same as 2e to the just I pi over 4. Because 9 pi over 4 is pi over 4 plus 2 pi, right? So there's no need to keep going. You've now found them all. One thing to notice, if you would graph these, it looks like this. Here's C0, sort of at a 45-degree angle here. You see that they're going to be spread evenly around the circle. Here's C1 over here, here's C2, here's C3. This is what always happens, it turns out. The nth roots of a complex number are going to be spread evenly out around the circle. The angle between them is this 2 pi over n. In the case of this particular example, n was equal to 4. So the angle between them was pi over 2. Okay, so I think this is the last page of these notes here. Yeah, so just a few observations before and a couple little definitions before we head out. We're now at a position where we can sort of, introduce some new notation. So, in real numbers, you talk about the power 1 over n for the nth root of a real number. So now we want to do that for a complex number. But we just noticed that, there's more than one 4th root. There are actually 4 4th roots. So if you were doing 10th roots, there would be 10 of them. So when we say z to the 1 over n, we mean it's going to be the set of all nth roots of z. And if we want to get a special root, we can maybe talk about the principal nth root. We don't have a special, notation other than to say C0 is the principal nth root. And this is also a notational convention for this course, but it's also true in the past. But so we won't talk about, so we'll never do this. For a complex number z, we'll never do this, the nth root of z like this. So that we just won't do that notation, because we're going to reserve that symbol, that square root symbol, for real numbers. So if r is a positive real number, then the nth root of r here will just be understood to be the positive nth root of r. But we're talking about a real numbered concept here. When you talk about the positive nth root of r, it would just be that positive real number that when you raise it to the nth power, you get back r. So you're not going to get n of these things. There's just one. So this thing's unique. So moral of the story is don't use this sort of thing when you're talking about complex numbers. Only do that with real numbers. And when you do use it with real numbers, you're talking about you're always talking about a positive number. Here I'm giving definition to something. I guess I already defined it before, but I want to, just for emphasis, when we talk about the principal root of a complex number, z naught equals r naught e to the I theta naught, it's just going to be that root c naught. We're insisting here that our angle theta naught, the one that we started with in our representation of z naught in the exponential form of z naught, that we started from the principal argument. So then if theta naught is the principal argument, c naught equals, let's see, that would be your nth root of r naught e to the I times theta naught over n. And then, you're doing c naught, so there's like this plus 2 pi times 0 over n, but, that's times 0, so it just goes away, and so it just collapses to this. This is your principal root. And then this last observation that I wanted to make before we take off is, it's just the same observation I was making when we were doing the fourth roots of 16, that all those roots are going to be spread evenly around the circle. So in general, it kind of looks like this. Like let's say here's C0, and this angle that C naught makes with the x-axis is that theta naught over n. And then you're going to have another, like C1 is going to be like here, and the angle going from C naught to C1 is that 2 pi over n. So then you're going to have another one over here somewhere like this, C2, where this angle is 2 pi over n. C3 would be like here. Go another 2 pi over n. And if you do this enough, you eventually come all the way back around, right? So dot, dot, dot. And you can tell because the angle is 2 pi over n, there's got to be exactly n of these things going around. There'll be one last one right here, Cn minus 1. And then again, when you go from Cn minus 1 to C0, that angle is 2 pi over n. Over n. So anyway, that's how the roots of a complex number are spread out on a circle, and then the radius of this circle is the nth root of whatever r naught is. All right, well, I'm going to stop there, and there's a lot to absorb in this lesson, so it's very helpful with all of these things to try to work as many concrete sort of examples. So it'd be a good idea for you to do something like, hey, why don't you get the cube roots of -8? See what those look like, or pick some weird complex number like 1 plus I, and then take the fifth roots of that and see what you get. Just practice it a little bit. And in the process, you'll have to calculate what the principal argument is, and you'll have to get these angles. And so doing these root examples is pretty good practice for everything that we've talked about today. And we'll have some examples like that on the homework exercises as well. All right, I'll stop there and talk to you again soon. Bye now.